We're gonna continue on here. We were talking chapter 10, I think. And again, chapter 10 was acids and bases. As we talked about, sort of the last chapter there before we hit organic, and a good number of formulas and stuff in this chapter. We talked about really sort of the Bronsted-Lowry definition of an acid and a base. An acid is a proton donor. And again, a proton is an H plus. And as we also talked about last time as well, H plus and H3O plus, which is the hydronium ion, are used really interchangeably in acid-base chemistry. They represent really the acid part of the solution. Bronsted-Lowry base, on the other hand, is a proton acceptor. And remember, this sort of gives rise to partners. So if this is our acid and water here acting as a base, it's going to send the H plus over to water. It will make H3O plus, and it will make a little A minus. And the acid on this side, again, its partner on the right-hand side is the conjugate base, while the base on the left-hand side, its partner on the right-hand side is the conjugate acid. And really, the importance of the relationship between those two is pretty much what happens in our acid-base sort of situation. The only deal or difference that there should be is one H plus difference. And again, in order for these guys to be pairs, that can be the only difference that there are. Typically speaking, in an equation, on the left-hand side, your acid and bases are found. On your right-hand side of the arrow, your conjugate guys are found. Your acid and bases are on the right-hand side. So as we go from our acid to our conjugate base, because it donated it, it will have one less H plus when it gets to the other side. And our base, since it accepted it, will have one more H plus when it gets to the other side and becomes the conjugate acid. We talked about Kw, which is the concentration of H plus times concentration of OH minus. And that does equal a constant value of 1 times 10 to the minus 14. And again, as I mentioned before, you could also write this as H3O plus and OH minus. So we could use this if we know either the H plus concentration or the OH minus concentration, which would be 1 times 10 to the minus 14 divided by the OH minus. Or if we want the OH minus and we know the H plus concentration, we can just do basically the same calculation. And we could actually compare the concentrations of the H plus and the OH minus to help us determine whether or not something is acidic, basic, or neutral. If the H plus concentration is larger than the OH minus, then obviously more acid than base there is going to be acidic. If the H plus concentration equals the OH minus concentration, it will be neutral. And if the H plus concentration is less than the OH minus concentration, which basically means the OH minus concentration is larger, it will be basic. A couple of things we talked about. We want to definitely make sure you use your exponent button when you're punching these things in. And also when you are comparing the H plus to the OH minus concentration, remember that if you have a negative exponent, the smaller negative exponent is the larger number. So just keep that in mind. We then got towards the end, I think, talking about the pH scale. And the pH scale runs from 0 to 7 to 14. Less than 7 is acidic. Above 7 is basic, and 7 there is neutral on the nose. And as you go from 7 to 14, you become more basic, heading in that direction, and more acidic as you go towards the 0 in that direction. To calculate the pH, it is equal to negative log of the H plus concentration. Once again, also same equation. If you want to use H3O plus in there instead, same deal. And once again, as we talked about as well, in terms of your calculators, it's important to know how to properly punch it in. So again, if you have a display calculator, you're going to pretty much punch it in exactly the way it's written. The negative button, pretty much, the log button, and then your number, probably with your exponent button in most cases. If you have a non-display calculator, again, this formula and pretty much the rest of them, you do have to kind of work backwards. So you got to start with really the number, and again, probably using your exponent button. You then need to hit the log button, and then you need to hit the sort of negative button there. So again, kind of display just like the things are written, non-display heading backwards. Remember, significant figures and pH, and it is the number of significant figures in the concentration value equals the number of decimal places in like the pH calculation. So remember that we're going from significant figures to decimal places, not significant figures to significant figures. So if your concentration, which is what this represents, if your concentration has two significant figures, when you calculate something like pH, it should have two decimal places. Again, two decimal places, not significant figures. And also if you're going backwards as well, as we'll talk about, if you have the pH and you're calculating the H plus concentration, and you have two decimal places, your concentration should have two significant figures going in the backwards direction. Any questions on any stuff there? All right, so we finished up on an example, I think. So I think this is where we left off. So speaking on the pH scale, it's based on the log 10, and for every power of 10 that it changes, basically the pH will change by 1. And if you have like an H plus concentration of 1 times 10 to the whatever the exponent is actually the pH. So if you had like the 1 times 10 to the minus 5, the pH would be 5. If you had 1 times 10 to the minus 6, the pH would be 6, and so forth. So for every power of 10 change that there is, the pH will change by 1. As the H plus concentration increases, the pH will decrease and become more acidic as there's more H plus in the solution than OH minus. Remember, that's another relationship we talked about, which is as the H plus concentration increases, the OH minus concentration decreases, and obviously vice versa. So as one goes up, the other goes down. So in that case, we would have a lot more H plus, a lot less OH minus, which is like the base part of the solution. And we would have a much lower pH because it's going to be more acidic. And vice versa, obviously, if the H plus concentration went down, we would see an increase in the OH minus concentration. And if we see an increase in the OH minus concentration, that means that we do see again that decrease in the H plus, and we actually will see a rise in pH again here because we have more OH minus than H plus. So the pH will go up and perhaps basic in that situation. Questions on that there? Now, there are a few different ways that you can measure pH. You can use a pH meter, which is a pretty good way of measuring pH. It has an electrode on it. It measures essentially the H plus concentration that's floating around in that beaker. What it really does in most cases is you calibrate it with some solutions that you say this is a solution of 4, pH of 4, solution of a pH 7 and 10, and they figure out the voltages, make a little calibration curve, and then you stick yours into your solution. It goes, oh, it's got a voltage of this, it's a pH of whatever it may be. But this is something that sort of directly measures the H plus concentration. Nice thing about it is it just spits you out an actual pH value there on the screen. Another common way is to just use pH paper. If you ever played with a pool or kind of done some pool chemistry, they sell those pool strips and you dunk it in the solution, it changes colors. Kind of same idea here. You dunk it in your solution or dunk the solution onto the pH paper, and then you just try to match up all the little colors and go, okay, it's a pH of 1, 2, 3, whatever it may be. Other things that we use sometimes in lab, not necessarily to measure pH, but just to know, again, if something's acidic or basic. We do, I think we talked about before, we use litmus paper sometimes. Litmus paper, basically, if it turns red, it's acidic. And if it turns blue, it's basic. And again, litmus paper doesn't really give you the pH or anything like that, but it does tell you whether or not, your solution there's acidic or basic. So sometimes we use that a lot of times where we don't really need to know the pH, but want to know if, is it acidic or basic, perhaps a solution. Here's our pH scale. And again, we see things like sodium hydroxide, which is a strong base. A lot of cleaners are also basic. And we also got some acid down here, which is acidic, and some vinegar, lemon juice, stomach acid. We have some pure water here at a pH of 7. If you check the pH water, that's maybe not pure water. Will it be a pH of 7? Will not. It'll probably be acidic, like in this range there, and it'll pick up some carbon dioxide from the air, especially if it's been sitting out a long time. And it'll make carbonic acid, and that'll increase the H plus concentration. So it's slightly acidic sometimes, especially if it's been out for a while, kind of in the open air. But if you have pure water, it will be 7. Sometimes people, if they really want it, kind of pure water, and they're doing something where maybe the pH is really important, they'll sometimes boil their water, and they boil the water because it makes the CO2 less soluble in the water, and the CO2 will go away, and it'll bring the pH back up to more like a neutral sort of pH. Now, I think we touched upon this at the very end when we were doing an example, but a reminder that there are some similar scales to pH, which is the POH. And the name does tell you what you need to calculate it. POH means you need the OH minus concentration to calculate it, just like pH means you need the H plus concentration basically to calculate it. It's calculated the exact same way. It is a negative log of the OH minus concentration. The nice thing about that is the pH plus the POH equals 14, which means, for example, if you're given just the OH minus concentration, you can calculate the POH, and then subtract 14 to get to the pH without having to do much work on it. So our pH equals negative log of the H plus. Our POH equals negative log of the OH minus concentration. This is also the problematic for a lot of people because I think we talked maybe a little about it, but just to remind you, when you're asked something like, hey, is the solution acidic, basic, or neutral? There is only one answer for that for a solution, but very commonly what people will do is they'll calculate the pH and go like, hey, it's above 7, cool, it's basic, and then calculate the POH and go, it's less than 7, so it's acidic, and the same solution is acidic and basic at the same time, and that cannot happen. So there should only be one answer to that. I've never had anybody give me all 3. I guess that's good, but sometimes I've had people give me both. The importance, and what I would highly recommend, is always look at the pH value, because that is the scale, as we just talked about, that pretty much everybody has in their head, that less than 7 is acidic, above 7 is basic, and obviously 7 is neutral. And the reason I say that is the POH runs opposite. So if you look at the POH scale, 0, 7, and 14, less than 7 on the POH scale is basic, above 7 is acidic, and at 7 is still neutral. So it does run opposite of each other, and I say probably everybody has this one in their head. So I wouldn't even look at the POH value in terms of determining acidic, basic, or neutral. Always look at the pH value and determine it based off of that. Any questions on that there? So KW, as we had just saw as well, H plus OH minus equals our 1 times 10 to the minus 14. Now let's talk about a couple other things that we could calculate here. If you have the pH value given to you, you could get directly from that the H plus concentration. So you could directly calculate the H plus concentration from the pH. To do that, that is the inverse log of the negative pH. On most people's calculators, when they hit inverse log, a 10 and a caret pops up, and you want to make sure it's negative pH, or how a lot of people do scientific notation incorrectly, which is why you definitely don't want to be doing that and that calculation, because you will be way off here. So you want to make sure you're using your exponent button in this case. To get to the inverse log, I would say on most people's calculators, that's a visit to the upper left corner where you have a second button or a shift button, and then usually your log button that has like a 10 to the x, and that is basically how you would do that. Just like all the other formulas, if you have a display calculator, you're going to punch it in exactly like that. So you would hit, if you have a display calculator, you would hit again your second or shift button, you would hit your log button, you would hit your negative button, and then type in the pH. If you have a non-display calculator, you're going to start with the actual pH first, then you would hit your negative button, then you would hit your second or shift and your log. And again, depending on which type of calculator you have, as to how you should properly put that in. That is for the calculation if you have the pH and want the H plus concentration. As we were talking about here, if you're doing that, however many decimal places there are is how many significant figures your concentration should have. In addition, as you might imagine, you could do the exact same calculation with the POH. So if you have the POH, you could directly calculate from it. The OH minus concentration is pretty much the same calculation. It is the inverse log of the negative POH. And again, on most people's calculators, a 10 and a caret gets popped up there when you hit the inverse log. So these are a few other sort of formulas you should add to your list here. And because there's so many different formulas here, there are a variety of ways to solve these problems depending on sort of which pathway you choose. They all should get you to the same answer, but you can obviously solve these problems in a couple of different ways, depending on how you're going there. Any questions on that there? And obviously, that would be the same way to punch it in down here as well. Yeah, so same thing, basically. Any questions on any of those? All right. Then let's try here. For each of these, let's just try out our calculators, make sure they work, I suppose. Yeah. Let's do the OH minus concentration for the first one. Let's do the pH. Let's do the POH, and is it acidic, basic, or neutral? For the second one, let's also calculate the H plus concentration, the pH, the POH, and also see how we're doing. Just split it right there. All right, we'll start guy on the left here. We pretty much want to solve for everything. So really at this point, I have two options. I have the H plus concentration. So I could use KW and get the OH minus concentration like we've done previously. I could also directly calculate the pH, and that's what I'm going to do first, actually. There is no really right or wrong move there, but I'm just going to take the pH first. So that's going to be pH is equal to negative log of 3.6 times 10 to the minus 9. And that's going to give me a pH here of negative log 3.6 to the minus 9. Whoops. Negative log 3.6 minus 9. There we go. You can give me 8.44 as our pH. Now that I have the pH, again, I still have the option of using KW to get to our OH minus. I could also get the POH at this point as well, since the pH plus the POH equals 14. So really our POH here would be 14 minus our pH, which would be 14 minus 8.44. And that's going to get us there 5.56 here. I still have my option to use KW if I wanted to, but now that I got the POH, why not try the new calculation, which is I could use the POH here and I could get the OH minus concentration from it. So because I have the POH, once again, I could get directly from that the OH minus concentration, and that's going to equal the inverse log of the negative 5.56. Once again, on your calculator should probably look something like this. punch it in one of the two ways I described on the previous page, and you should get here. If you hit the right button, unlike me, there we go. We'll go with an OH minus concentration of 2.8 times 10 to the 1, 2, 3, 4, minus 6, and that does need a molarity as it is a concentration. Question on that. Once again, to punch that into your calculator, if you have a display calculator, you would go again second or shift log, most likely negative 5.56 and hit equals. Again, if you have a non-display, you would start with 5.56, then hit your negative button, then hit your second button, and then hit your log button. And again, one of those two ways should hopefully take care of 99.9% of everybody probably that's sitting here. Any questions on that one there? Yeah. Yeah, it's okay. It should be fairly close. There will be perhaps a little bit of a difference depending on where you round and stuff like that, but it should be very, very close. You shouldn't be tremendously off, so that would be okay. Yeah. Question? Yeah, so we went backwards here based on how I did the calculations. So when we're going backwards from the POH to the concentration, we would look at the POH, which is like the pH. It has 2 decimal places, which means my concentration should have 2 significant figures. So we go from decimal places to significant figures there on that way. Yeah. And here, same thing. We went from significant figures, which is 2, to 2 decimal places here. Again, not significant figures as you go from one to the next in that case. By the way, this is acidic, basic, neutral. It is basic, and that's the one you should look at there, right? It's above 7, the pH, and it should be basic. Any questions on that? Again, as I mentioned before, and as was the question earlier, you could definitely have used the KW. And again, depending on rounding and stuff like that, it should get you an answer pretty close to that going in that direction. Yeah. Yeah. Are you talking about this right here? Yes. That's just usually, I just write that because that's usually what you'll see on your calculator if you have a display calculator. So that's usually what it kind of looks like. So usually when you hit the inverse log, or basically the second button or shift button log, it usually on most people's calculators pop up a 10 and like a caret, or maybe pop up a 10 and a little guy blinking up towards the top, and that's usually what it kind of looks like on your screen on most people's calculators. Now, other questions? All right, then let's take a look at the one next door here. And here, because we have the OH minus concentration, we have really a couple of options as well. We could get the H plus again using KW right off the bat. We also could calculate the POH here. So let's do that. I'm going to do a POH first. So POH will be negative log of the OH minus concentration. And that's going to give me negative log of 9.2 times 10 to the minus 2 in this case. And that will get me, again, make sure you're using your exponent button. Looks like a POH of 1.03. At this point, once again, I could still get that H plus concentration, but just as easily, I could also get the pH, because all I have to do really is just track 14 basically here. So my pH will equal 14 minus the POH, and that'll give me 14 minus 1.03. That's going to give me a 1296 on the pH. And lastly here, I could, now that I have the pH, also do the inverse log, or we could use our KW. So if we did the inverse log, our H plus concentration would equal the inverse log of the negative pH. And again, on your calculator, it'll look probably something like this when you pump it in. Or you could also, again, return back to our KW and divide it by the original concentration that was given to us. And either one should give you basically the same answer. And if we do that there, looks like we'll call it 1.1 times 10 to the minus 13, and we do need a molarity there. And again, if you did it with the KW, you really should get something pretty darn close or identical in this case. Any questions on that? Yeah. Okay. Yeah. I took the negative log of it, like to calculate the pOH. Yeah. So, yeah. So, no, so it's this one right here. It's actually this equation right there. So the pOH is equal to negative log of the OH minus. And that's pretty much identical to this calculation, which is the pH is minus the log of the H plus. And it tells you what you need, OH and H there. And that's how we get to each of those numbers. And this is punched in on calculator, negative button, log button, and then either your H plus concentration or your OH minus concentration. Yeah. Not to be confused with this one here. This is where you have the pH or pOH and you want the concentration. So that's the opposite of it. So log is like I need pH or pOH. Inverse log is like I need concentration, basically. Yeah. So it's kind of opposite. But other questions on that? And this would be acidic, basic, neutral. This one would be basic as well. Again, looking at the pH, which is 12.96, definitely above 7 in this case. Yeah. Any questions on that there? Fun with calculators. Let's try some more. Yes. All right, so we have a pH of 5.67. Let's just practice our calculator some more. Let's do the pOH. Let's do the H plus again. Let's do the OH minus concentration. And is it acidic, basic, or neutral? Let's see what you come up with. Practice punching it in. Take a look. So once again, in this case, we are given the pH. And since I did change the question here, we do have a couple of options of things that you get directly from that. Once again, directly from that, you can get the H plus concentration, and that's a concentration, which means that's the inverse log move. We could also get the pOH directly from that, and that is our 14 minus the pH there will give us our pOH in that case. So we do have a couple options as to which way we can go. I'm going to do the pOH first, which means I'm going to go my pH plus my pOH is equal to 14. That means my pOH would equal 14 minus the pH. So 14 minus 5.67, going to give us here 8.33 as our pOH. I am now going to actually do this one, which is calculate the H plus concentration. And once again, from the pH directly, you could calculate that. And that is the inverse log of the negative pH. Once again, when you pump that into your calculator or punch it into your calculator, it will probably look something like this, obviously with our number in this case, which is 5.67. And that's going to give us here. And make sure also you're using, again, the negative button, not the subtract button. Yeah. So was going to say carefully, but I just feel like the right answer there. So let me try it this way. So we're going to do, if you have a display calculator, you're going to want to hit again either the second button or the shift button top left, usually on most people's calculator. You then would hit the log button, and then you would hit your negative button, and then you would go 5.67 and hit equals. If you have a non-display calculator, you would start with the number 5.67. You then would make it negative by hitting the negative button, and then you would hit your second or shift button, and then the log button. Yeah, so one of those two ways should get it there. And if you do, you will get 2.1 times 10 to the 1, 2, 3, 4, 5, 6 minus 6. And by the way, on my calculator, I do not have a scientific notation. I got a bunch of zeros, 0.00000216. So it may obviously not give it to you in scientific notation on your calculator. Question on that there. Yeah, so again, on my calculator, this is what it looks like. And that's again, I just converted it to scientific notation, and hopefully I didn't lose a zero there along the way there. I think I got them all. In this case, in terms of significant figures, we have 2 decimal places, so 2 significant figures on our concentration going backwards. Now, at this point, since we also want the OH minus, we do have 2 options. Since I just got the H plus concentration, I could go classic and do a KW calculation. I could also, since I do also have the POH, do a similar calculation and do the inverse log of the negative POH, which again punched in pretty much identical to how we did the previous one there, just using obviously this number here. And either of those should get you hopefully to the same destination there. So maybe I'll just do that. So I have it there. And you'll end up with perhaps like a 4.7 times 10 to the minus 9 molar as your OH minus concentration. Or if you have a calculator like mine, you will end up with a bunch of zeros and a 5 at the end because it ran out of space, basically, unless you put it into scientific notation. So on my calculator, pretty much all zeros until the very end, and there's a 5, with a decimal point. And again, it just ran out of space. But if you put in scientific notation, it will come back to 4.7 times 10 to the negative 5, a negative 9. Question on that there. Okay, so we also want to know acidic, basic, or neutral. In this case, this one is acidic, as we were given the pH to start with, and it is less than 7. Any questions on any of those calculations? Yeah. Yeah, so on most people's calculators, including mine, the one I'm using here, when I did the either one really for this last calculation, either way, on my calculator, pretty much this is what it looked like. It was 0.1 and like that basically, and that's fine if you gave me that as like 5.0 times 10 or whatever it is. If you know how to do it on your calculator, you can turn your answer into scientific notation. When you do so, it will turn into basically this number here. It's like 4.68 times 10 to the minus 9. It just does that because your calculator runs out of room basically, and just rounds up the last number to a 5. But if you could turn it into scientific notation on your calculator and redo the answer, you'll see like 4.68 times 10 to the negative 9. But if you can't, no worries, 5.0, and that'll be fine. Yeah. Other questions? It would be, because those are concentrations, so you would need the molarity. pH, POH are just numbers, so no units on those. Yeah. Other questions on that? All right, let's see here. Let's try another one here. pH is 3.14. What is the H plus concentration here? Well, we just do the H plus to see what we get. So let's take a look. Once again, we have the pH here, and really we have nothing else given to us. So unless we want to start calculating a bunch of things, we might as well just go right into the equation so we could calculate the H plus. So once again, pH means you could directly get the H plus concentration from it. And once again, that is the inverse log. So anytime you need concentration, inverse log. Yeah, no concentration, just log. Yeah, it's a good way to maybe remember it. Negative pH in this case. And once again, you would hit your second, you would hit your log, you would hit your negative and 3.14 and hit equals. Again, if you have a non-display, 3.14, then hit the negative, then hit the second, and then hit the log. And one of those two ways should hopefully get you to again, I'm just going to turn it into scientific notation. It's decimal form on my calculator, 7.2 times 10 to the 123-4 molar. Question on that one there. It does. So we're going backwards in this case. So we're going from pH, which means we have two decimal places. So those two decimal places means when we get to the concentration, we should have two significant figures. So decimal to significant figures. When you're doing this calculation for the H plus or the OH minus from the pH or the POH, you do have to make your number negative. And this is not really on a lot of people's calculators, that's like the negative button. Or some people have this button as well, right? They have that as like the negative button. So if you have that one, that's what you want to use. Or you have the plus/negative, that's also negative button. The only one you do not want to use is the subtract button because you will get the wrong answer, obviously, or it might get an error or stuff like that. So yeah, if you obviously have that as your negative button, use that. Same thing here. If you don't have a second button, but you have a shift button, that's also the same button basically on most people's calculators. And some may even have a dedicated button, like mine actually has a dedicated button for the inverse log and stuff like that. But most people usually have to do the shift and log type of thing on the calculators. Yeah. It's decimal to significant figures is when you're going from pH or POH to the concentration, H plus or OH minus. If you're going the opposite way from like the H plus concentration or the OH minus concentration to pH or POH, you're going to go from significant figures to decimal places. And this one's the opposite of that, going from decimal places back to significant figures. So it works the same, just depends on which direction you're kind of going. So if you have pH or POH, and you're going to either H plus or OH minus concentrations, it's decimal to significant figures. And if you're going opposite, it is significant figures to decimal, going in the opposite way. Other questions? All right, so let's take a look then at one more here to make sure, hopefully. Oops. What is the OH minus concentration if we have a POH that is 5.67? Okay, so on this one, we have the POH, which is 5.67. We definitely get the OH minus from it. So in this case, we are going to punch in our inverse because we're looking for a concentration. So our OH minus concentration equals the inverse log of the negative 5.67. Once again, second log negative, whichever button you got, 5.67 equals. are again 5.67 negative and seconds and log. And that should get you here 2.1 times 10 negative 6. Yeah, 1, 2, 3, 4, 5, 6 negative 6. Oh, period. Question on that one there. All right, so obviously you need to be able to calculate pH, POH, OH minus concentration, H plus concentration. Obviously, there's a few different ways you could do it depending on sort of which path you choose. Most people frankly screw up because they're not sure how to punch it in or which one goes with which. So once again, if you need a pH or POH, it's just the log one by itself. If you need a concentration, H plus or OH minus, it's the inverse log. Or alternatively, you could also use KW if you have a concentration given to you. Any questions on that? By the way, here we were going from POH, which is decimal places, to concentration, decimal to sig fig. So 2 decimal places, 2 significant figures going backwards. So that's it. Questions on those there? All right, continue on. First off, though, any questions on these calculations? Again, it's really important to make sure you understand what calculation goes with what. That's, again, a very difficult thing for a lot of students. And then secondly to that is you got to make sure you know how to properly punch it in once you figure out which one you should be using. Again, there are multiple pathways to get to answers depending on which way you choose. Just choose a legitimate pathway and make sure you know how to punch it in. And really, they all should get you the same thing. If you have a little bit of difference, it's not going to be a big deal with some slight rounding, but it should really definitely be in the same ballpark. Any questions on any of that there? And again, if you still are not sure what button on your calculator to hit, just come and see me. Yes, I'll help you find it, hopefully on your specific calculator as well. All right, we're going to continue on here. Maybe there's something there. All right. So we're going to talk about a pH of, say, a strong acid. Now, up until this point, we've sort of been given like generic sort of concentrations like H plus or OH minus, but you may be given a actual formula for like a strong acid or even a strong base. And a reminder that we talked about some strong acids in this chapter, and a good list to sort of remember or know or refer to. Again, hydrochloric acid is a strong acid, nitric acid, sulfuric acid, perchloric acid, hydrobromic acid, and hydroiodic acid. So that's sort of a list of basically 6 strong acids. I would say probably with certainty in most cases, 99.9% of the time, if it is not one of those acids, it's probably a weak acid. So that's a good way to know, are you dealing with a strong acid or a weak acid? By the way, strong bases as well typically will have hydroxide in it. And again, on the periodic table, like lithium, sodium, potassium, hang a right to calcium, a little bit of strontium, some barium as well. Any of these guys here that have hydroxide in it typically are going to be your strong bases. Now, because they're strong acids, our strong bases, they will 100% break apart. So if we did have something like hydrochloric acid in solution, as we've talked about, it will 100% break apart into an H plus and a Cl minus. And you will have none of the HCl units still together. Now, when we talk about pH, right, it is the H plus concentration, which is really the most important thing to try to figure out in order for you to calculate the pH of, say, a strong acid. So, for example, if we had a 0.1 molar solution of hydrochloric acid, what we would want to figure out is what is the H plus concentration in this hydrochloric acid. And this is something we talked about when we talked about concentrations, right? It is a 1-to-1 relationship, right, between the whole thing and the H plus, which means the concentration of the H plus would be 1 times 0.1 molar, or still 0.1 molar, which means that's really all we would need in this case to calculate the pH. And the pH here would be negative log of 0.1. And if we pop that in there, and here we are looking for pH, so it is log, right? So as we talked about, no inverse log on this one, so just log, negative log 0.1 gives us a pH here of 1.00, which is definitely an acidic pH in this particular case. I will say the good news is most of the strong acids are monoprotic, which means they have one hydrogen, which means in most cases, if you know the concentration of the strong acid, you know the concentration of H+. You basically can just go right into the pH equation. How's that work for a base? Let's just say we have sodium hydroxide, which is a strong base. When it breaks apart, it will give you a sodium ion and a hydroxide ion. Once again here, pH is related to the H+ concentration, but there is no H+ in this, but we do have OH-, and we can calculate the OH- concentration, which means we can figure out the OH- concentration, which is helpful because then we can figure the POH, and then we can subtract 14 to get to the pH. So here with a strong base, because it's also going to 100% break apart, you can figure out the hydroxide concentration. You could calculate the POH and then subtract 14 and get yourself to the pH. So you could do this with a strong base or a strong acid. In either case, you could actually calculate the pH of those solutions. Now, if it is not a strong acid or it's not a strong base and it's a weak acid or weak base, and you need to calculate the pH of it, you should go take another chemistry class because that won't happen here. So it's a lot more complicated. So anything that's pretty much given to you probably in this class as a formula of a acid or base, you probably can 100% of the time assume is going to be a strong acid or strong base, and you can calculate the pH for, I guess I should say 99.9% of the time, you could probably assume that. We were not going to talk about how to calculate the pH of a weak acid or weak base. It's way more complicated, and we're not going to get into any of those type of calculations. So I would again say in here, if you're given a formula for an acid or base, probably safe assumption is going to be strong. Just need to figure out the H+ or OH- concentration, and you can get to the pH. Any questions on that there? All right, so why don't you try this one? Why don't you also calculate the pH of a 0.025 molar? It is not going to stay together at all. It will 100% break apart into H+ and perchlorate actually here. And we know that the concentration of the whole thing here is 0.025. Remember, in this case, for the pH here, the H+ is the important thing. It is, again, a 1-to-1 relationship between the whole thing and the H+, which means you take the concentration times it by 1 or really keep it the same. And that will give us our concentration of H+, which, again, here is all we really need to go into our pH. So our pH will be at negative log of 0.025 and 1.6, I think, maybe 1.60 here. And that is definitely an acidic pH, which is good because that's an acid. So again, if you got a basic pH here, that's not so good. Any questions on that there? Now, when we look at the second one, we have hydroxide. So that's barium hydroxide, which means it's a base. It also will 100% break apart in solution. And when it does, we will get a barium ion, and we will get actually 2 hydroxide ions. That is what the 2 means. There's 2 of them. And that's important because, as we talked about with molarity, we are looking at the hydroxide here. And that is a 1-to-2 relationship, which means in order to get the proper concentration for hydroxide, you need to multiply it by 2. Get twice as much there. That means that the proper concentration for hydroxide would be 2 times 0.025. We'll give you 0.05 molar. It's our hydroxide concentration. Now that you have the hydroxide concentration, remember that you cannot get the pH directly from that. You could get the POH, right? Because that's the OH minus. So we could first calculate the POH, which is negative log of the OH minus. And we could do that because that is what we have. Negative log of 0.05. And that's going to give us here a 1.30. Now, if for some reason you thought this was the pH, this definitely should not make sense to you because that would be a acidic pH and this is a base. So again, hopefully if maybe you thought that, that would then ring true to you. We can then get our pH by taking pH plus our POH is equal to 14, which means the pH will equal 14 minus the POH, which is 1.30. And if we take that, we'll get a 1270, which definitely is basic and makes sense in this case. So in this case, because we do get twice the amount of hydroxide, you do have to adjust the concentration of hydroxide to get the proper amount. It's like we talked about it with solutions and concentration, I think, back then. And then you can get the POH. I would say out of the two, probably if you come across a strong base, especially those that have a group 2 guy in it, that's probably the one you might have to look at to adjust. But other than that, most of the time, it may just be straight up the same number as the whole thing. Any questions on either of those there? All right, so we're going to talk then about buffers next and what they are, how they work, all that good stuff, I think. All right. So let's talk a little bit about buffers and a buffer solution. Good talk. Let's talk a little longer, maybe. So first off, a buffer solution is a solution that will resist changes in the pH even when you add additional acid or base to that buffer solution. And when we talk about changes in the pH, we're really talking about very big jumps in the pH. So if you have a buffer and you add more acid to your buffer, it should be able to maintain its pH about where it's at without it jumping really far down, or if you add base to it, without it jumping really far up. One of the first misconceptions that a person has about a buffer is that it is a neutral solution, and that is not really the definition of a buffer. You can make a buffer at any pH you like from 0 to 14. You could choose it and make it at any pH you like. What a buffer solution is whatever pH it starts at. Let's just say it starts at a pH of 5, and you add some acid to it. It will pretty much stay at a pH of 5. It'll go down a little bit. Maybe it drops to like 4.95, 4.9, but it will not go from like a pH of 5 all the way down to like a pH of 1. So you won't get this really big jump in pH, but it's able to basically maintain its pH. Also, if you have that buffer that was a pH of 5 and you add some base to it, it basically will stay at about 5, but maybe it goes up a little, 5.2, 5.02, 5.2, but it will not go from like 5 all the way up to like a pH of 13 or something like that. So if you make a buffer correctly and you add acid or base to it, it is able to basically maintain the pH at which it starts at. And that can be really any pH you choose. So it doesn't have to be a neutral solution. And that's a very common mistake that people say about, what a buffer is. It's always going to be a neutral solution, and it's not. A buffer is made up of one of two combinations, which is really important for how a buffer actually works. So it is either made up of, a buffer is made up of a weak acid and the salt of its conjugate base, or you can have a buffer that's made up of a weak base and the salt of its conjugate acid. What is a salt? The salt's just an ionic compound. So it's basically, what we're talking about here is basically your Bronsted-Lowry definition. Yeah, so those two things, the only difference really between those two things is an H plus. So again, the only difference between these two is an H plus. The only difference between these two is an H plus. Now, will also be some other ion as well, but it's not important, like a potassium, a sodium, or something like that. You cannot have a buffer that is made up of a strong acid or a strong base. So there's no possible way that you can make a functioning buffer out of something that is a strong acid or strong base. It has to be a weak acid or weak base. So this is where knowing those 6 strong acids come into play. If it's an acid that's not one of those, it's probably okay to make it a buffer out of it, because it's probably going to be a weak acid. Probably your most common weak base is ammonia. So ammonia is probably your most common weak base. You don't always have to be ammonia, but again, that's probably a very common weak base. Some weak acids are things like acetic acid, hydrofluoric acid, nitrous acid. You know, there's a bunch of them along the way, HCN, and so forth. So there's a bunch of very much weak acids, and again, any of those that are not the 6 probably going to be weak, and again, a good choice. So what does it mean to have a buffer, and why do you need those things in there? Why can it not be a strong acid and it has to be a weak acid or weak base? It's because in order to have a properly functioning buffer, you need to have inside your buffer an acid part of the buffer and a base part of the buffer. So you got to have both of those things floating around in the solution to begin with before it could actually work as a buffer. So the reason a weak acid, for example, will take the classic acetic acid, which is basically your main component in vinegar, is a weak acid, also a weak electrolyte, like we talked about. And if you remember, weak electrolytes, when they go into solution, will mainly stay together but break apart a little bit. So this guy will break apart into some acetate and some H+. This is a weak acid and its conjugate base. And for example, if I had sodium acetate, that would be the salt of its conjugate base. Or potassium acetate would be the salt of its conjugate base. The sodium or the potassium makes it a salt. It just balances out the charge. The sodium or the potassium is not really doing much. These 2 guys will be in solution and be able to stay in solution because of that weak acid. Now, if you try to make a buffer out of hydrochloric acid, when it goes into solution, it's a one-way street that's going to break apart into H+ and Cl-. This is basically your acid, and this is your conjugate base over here, which means you have none of this in the solution anymore. You would only have a base part in your solution, which means it's not going to be able to function properly as a buffer. So that is why a buffer cannot be made up of a strong acid or a strong base, because you will frankly only have one of the components necessary for that buffer to work correctly. Now, again, if you had something like hydrofluoric acid, also a weak acid, breaks apart into H+ and F-. Right? So if you had a beaker of either of those guys, when you would take something like HF and maybe some sodium fluoride, right? That is a weak acid and its conjugate base. And this is what's referred to as the salt of its conjugate base, because the sodium is present. The sodium is frankly doing nothing. It is just hanging out. And this is really Na+ and F-. That is actually the functioning part of the buffer, is the F- part of it. The sodium is just there, again, just hanging out, balancing out the charge. So when you go into solution, you will have HF that will set up this equilibrium with arrows in the beaker. Not really, but we'll pretend. And you will have both of those things floating around that solution. You will have this part of the buffer that is an acid part of the buffer. And you will have this guy here, which is its conjugate base, and the base part of the buffer. And both of those guys will be able to stay in solution in good amounts, because in addition to the HF, you're going to dump in some sodium fluoride, which is going to provide a lot more fluoride. and you're going to have a pretty good concentration of this guy and a pretty good concentration of that guy floating around in the solution as a buffer. And that is essential for how a buffer is able to actually work, is that you have an actual acid part and a base part of the buffer. Any questions on that? Same thing with acetic acid. If you did the, say, acetic acid buffer with like sodium acetate, once again here, it is really the acetate part that is the buffer part of it. The sodium is not doing much. And if you had a beaker of these two things mixed together in the proper proportion, you will have the acetic acid set up this equilibrium. Where once again, we will have the base part of the buffer and the acid part of the buffer. And now you have something that is good to go and ready to work as a buffer. Once again, if you try to make it like HCl and sodium chloride, when you would do that in the solution, you pretty much will just have H plus, Cl minus, some more Cl minus, and some sodium ions. You will not have any of these guys in there because it's a strong acid and it's not going to stay in solution, which means the only thing you really have in here is a base part. And that is why this cannot be a buffer. So that is super crucial for how a buffer is able to work, is having both of those things in your beaker to start with before you do anything to it. Any questions on that so far? So let's actually talk about how a buffer sort of works. So let's take a look first off at if we added acid and base, additional acid and base to a non-buffer. So let's talk about what would happen if we take a non-buffer solution like our good friend water. Water is not a buffer. So if we were to add a strong acid to water, we know that it is going to 100%, as we've been talking about, break apart into H plus and Cl minus. That means if we take our water and we add our HCl, we just put into there a bunch of H pluses and Cl minuses. So I just generated a bunch of H pluses. I just made a lot of H pluses. That means that the concentration of H plus is going to go up. That also means concentration of OH minus will go down. And that also means the pH will go up or down. Will go down. The pH is going to go way down. So for example, let's just say we had nice neutral water. You put some HCl into water, you'll see it go from a pH of 7 down to like a pH of 1 or 2, depending on how much you put in there. A really big drop in the pH, because basically what you did is just litter that water with a bunch of H plus, increase the amount of H plus in that solution really, really quickly. And we see a really big jump in the pH because of that. Now, if we take something like sodium hydroxide and we add some sodium hydroxide to water, same thing's going to happen here. Sodium hydroxide is a strong base, which means it's going to 100% break apart into sodium ions and hydroxide ions. So if we take our beaker and we have some water and we dump some sodium hydroxide in there, we're going to make some sodium ions, but we're also going to make a bunch of free hydroxide ions, right? So what we just did in this situation is we just made a lot of free OH minus, right? And because of that, the concentration of OH minus goes up, concentration of H plus goes down, and the pH goes up, right? A lot more OH minus than there was before. So once again, maybe it started at a pH of 7, and now it jumps to like a pH of 12 or 13, depending on how much you dump in there. So we're going to see this really big jump in it. And it's really because if we think about the equations, right, for pH and POH for example, which obviously affects the pH of the solution, is, as we increase those concentrations, we're going to see a really big jump or change in the pH because we have a lot more free H plus and free OH minus. And that's really the important part of it, is that we have now introduced into here a bunch of free of these ions floating around freely in there. Any questions on what happens in a non-buffer situation? So let's see what happens when we add both of this acid and base to an actual buffer. So I'm just going to choose, for the sake of arguments here, I'm going to go with the HF and sodium fluoride buffer because it's less letters to write. Everybody else uses acetic acid and sodium acetate in most cases. Once again, this is a weak acid and the salt of its conjugate base. And again, here it is the F minus that really is the functioning part of the buffer. Again, the sodium is what's referred to as a spectator ion. It's just hanging out. It's not really doing much in terms of anything, but it's really the F minus part. And the difference between HF and F minus is a H plus, right? Or Bronsted-Lowry definition. So that again is what you need. So what happens is if we have this buffer, again, we will have HF, we'll have some H plus, and we will have some F minus in there. Once again, we have the base part of our buffer, and we have the acid part of our buffer. This is our buffer. So now when we take something like hydrochloric acid, like we saw on the previous slide there, and we add some hydrochloric acid to our buffer, it is actually going to react. So when I add an acid to my buffer, will it react with the acid part of the buffer or the base part of the buffer? The reactions are called acid base. So when I add this acid to my buffer, it is going to find the base part of the buffer, and they're going to actually do a reaction. So what's going to happen is my HCl will then react with my sodium fluoride, which is really my base part of the buffer, right? And this is a double displacement reaction, right? We're going to swap some partners here, and we're going to get a little HF and a little sodium chloride in this case. So what happens is when we dump this in here, it's going to go find the base part and actually do a reaction. Now, a couple of things here that happened is we actually made more HF that was in the buffer to begin with, and that always happens. So when you have a buffer, you actually will use part of the buffer up, but you'll then actually make the other part of the buffer. So it's kind of like you use a little bit up, but then you make the other part of the buffer in that. So this was already there, so that's not going to mess up the pH. We have sodium chloride, which is a neutral salt. That's not going to mess up the pH. It's really what we do not see here that we did see when we added the HCl to water. So what did we see here that we don't see in the other reaction? That's really important for pH. Right. In this case, when we added the HCl to water, which is a non-buffer, we just dumped a ton of H plus in there. In the case of adding it to our buffer, we made no free H plus in this case, right? So no more free H plus was made because that H plus got tied up with our base in this case, right? So it's not freely floating in there. Because we didn't make any more free H plus, that means that the concentration of H plus stays relatively constant. And if the concentration of H plus stays relatively constant, then the pH should also stay relatively constant as well. So it's because it's able to react with the base part of your buffer. What it does is as that H plus and Cl minus comes in, that H plus gets tied up here with the F minus and actually makes some more HF in this case. And what that does is it keeps pretty much the amount of H plus we had in there originally about the same. And that's what keeps the pH about the same. I say relatively constant because, as I mentioned before, if you were following the pH, you would see it come down a little bit. but you would not see a giant drop in pH. So again, in this situation, maybe the pH goes from whatever the pH started at, we'll go with 8.25, and maybe it drops down to 8.2 or something like that, but it doesn't go from like 8 to a pH of 1. So you won't see this really big jump in pH because the amount of H plus that just entered that solution is pretty much the same amount of H plus that was there to begin with. Any questions on that there? So now if I take this same buffer here and I add my sodium hydroxide to it, let's see what happens in that case. So once again, we have our buffer, we have our HF, we got our H plus original concentration, our F minus, once again, our base there, our base part of our buffer, we have our acid part of our buffer, and now we're going to add some sodium hydroxide into this. So I'm going to add some sodium hydroxide, which is basically a source of sodium and hydroxide. That is a base, which means it will react with the acid part of the buffer or the base part. It is going to react with the acid part of the buffer, which is why it's important. Both things are actually in there. So when I do my sodium hydroxide, it will react with the acid part, which is the HF, and it will do just a normal acid-base reaction, which means also double displacement. You're going to make some water, and you're going to make a little sodium fluoride. Once again, I made water, which means it's not going to mess up my pH. I, again, like above, made more of the other part of the buffer, which is not going to mess it up. So what's happening here is when this OH minus goes in for a swim, it will actually react with this and hit that H off of there and make just some more water basically at this point. It is once again what we do not see here that we saw when we added the OH minus to water. When we added the OH minus to water, we had a bunch of OH minus basically being made, right? So when we add that sodium hydroxide to water, we produce a lot of OH minus really quickly. In this case, we do not see any free OH minus. And because the concentration of OH minus stays relatively constant, that is tied to the concentration of H plus, because as one goes up, the other goes down. And in this case, the H plus will also stay relatively constant. And thus our pH will stay relatively constant as well. Again, if you're following the pH here, you will see the pH go up a little bit, but not a giant jump in pH, but it will go up a little bit. So ultimately, the way a buffer works is because it has both of those things in the solution to begin with. The buffer itself has the acid part of the buffer and the base part of the buffer. When you add additional acid to the buffer or additional base to the buffer, it's able to prevent the formation of free H plus or free OH minus, both of which, because they don't get made, keeps the concentration of H plus relatively constant, and that's what allows it to keep its pH relatively constant to where it's at. And you do not see giant jumps in pH because of that. Any questions on that? So essentially here, you could think of a buffer like this. So you have a buffer and you have a acid part of the buffer, which is sometimes just abbreviated HA, and a base part of the buffer, which is our A minus. And if you add some acid to your buffer, it's going to react with the base part, but it's going to make some more of the acid part. So dramatic drawing there. Your acid part of your buffer will increase. Your base part of your buffer will decrease. And if you add some base to this buffer, it will react with the acid part and the base part of the buffer will increase. And the acid part here will decrease. There is a limit to how well a buffer could work. What happens if you don't follow instructions, which I'm sure would never happen, and you just keep adding acid, for example. Let's just say I just keep adding acid to my buffer. What's going to eventually happen? Yeah, you're just every time you add acid, right, we're eating up the base part of the buffer, right? So you keep adding it, you keep adding it, keep adding it, open the bottle, dump the giant bottle in there, right? You're eventually going to blow right through the base part of your buffer, which means at that point, if you continuously add more acid, you're just dumping in a bunch of H plus at this point, right? And at that point, you will see a really big jump in pH, right? Because you've now basically blown through your buffer. So there's what's referred to sometimes as buffer capacity. There is a limit to how good a buffer is. And also when you make a buffer, you typically want to make it appropriately in terms of its concentration to handle the concentration of your acid or base that you add. So for example, if you made like a 0.1 molar buffer and you were supposed to grab like the 0.1 molar HCl, but you grabbed like the 18 molar HCl and you dumped it into your buffer doesn't stand a chance. It's going to blow right through it. There's not enough buffer components to handle the amount of acid that's coming in. So it's really important when you do make a buffer to pick one and make it appropriately in terms of its concentration so that when you do add acid or base to it, you really can make sure your pH doesn't jump greatly. Buffers are really good because when you make a buffer, for example, you'll never be able to make it exactly to the pH you want, but because a buffer could resist changes in pH, you could actually take acid or base and slowly add drops to it, and you could actually dial it into the exact pH that you need. So let's just say you wanted to make a 5.5 buffer and you made it like you calculation. And as you know, when you calculate something, you can't weigh out everything exactly and stuff like that to get the exact number. You put it all together and you end up with a buffer that's a pH of 5.4 rather than 5.5. You could just take some base and add a little bit of base to it and dial it right into 5.5, and you'll have a buffer at exactly what you need because it will not fluctuate greatly because it's able to withstand really big changes in pH. Any question on buffers? All right. So that is acid and bases, but there's one other topic we need to talk about before I forget. So we will start talking about it now, which is our friend Le Chatelier's principle, where they moved into this chapter, and years ago it used to be way earlier on, and I always forget to do it. So I'm going to try to remember not to forget here. So we're going to talk about Le Chatelier's principle, which actually involves a specific type of reaction, and it's actually one of these reversible type reactions. So for example, if you have 2A plus 3B goes to C plus 2D, for example. And let's just say these are all gases or something. And this is a reversible reaction, which means we do have arrows heading in both directions. And as you go from reactants to products, that is what is sometimes referred to as the forward direction. But in these reversible reactions, what happens is at some point, you'll build up enough products that they will actually come together and decide, well, we want to go back the other way. And you'll start to get our products heading back to our reactants. And that is what is referred to as the reverse direction. And this will happen until what is reached is known as chemical equilibrium. And chemical equilibrium does not mean equal, which the name might imply. What chemical equilibrium means is it does not mean, again, that you have the same amount of everybody on each side, which again, equal kind of implies that. What it actually means is the rate of the forward direction will equal the rate of the reverse direction. So just as quick as it goes to the product side, those products will come back the other way. So you got everybody going back and forth at exactly the same rate. What that actually does is whatever concentration or pressures, if they happen to be gases, that everybody's at that point, they pretty much will just maintain. So, you know, if they reach equilibrium and this guy is at 2 molar and this guy is at 1 molar and this guy's at 4 molar, this guy's at 3 molar, when they reach equilibrium, everybody will pretty much just keep those concentrations because it's going back and forth at the same rate. So just as soon as you lose something, it comes right back. So everybody just gets locked into their concentrations at that point. Now, there is a relationship in these type of reactions, which are known as the equilibrium constant. And that is K, which is the equilibrium constant. And that is capital K, by the way. Small k is the rate constant. So this is capital K, which is equilibrium constant. And basically you calculate K by taking the concentration of your products divided by the concentration of your reactants. And when you have an equation such as the one I wrote there, you actually can write the expression as the concentration of C times the concentration of D squared divided by the concentration of A and the concentration of B cubed. You actually take the coefficients. So for example, you have this. You could write the equilibrium expression by or taking our products. And the coefficients in the balanced equation become the exponents. Like so. And that's where I got all these numbers from. They are the coefficients in the equation. And obviously this guy is 1, so there's nothing really written there. It's assumed to be 1 in this case. So in general, you take products over reactants. The things that go into the equilibrium constant expression, you include only things that are aqueous or gases. Anything that is a solid or a liquid is not included in K. Now, an equilibrium constant is actually just a number, and the number tells us a couple of things. It tells us, for example, if we have a large value of K, when I reach equilibrium, would I mainly have reactants or products if I had a large value of K? So to calculate K, we take products divided by reactants. If I have a large value, should I have more reactants or products? Products, right? Because large number on top divided by small number gives us a large number. So we would mainly have products. And if I have a small value of K, I would mainly have reactants for the opposite reason. Bigger number on bottom, smaller number on top will give us a smaller number. So you could calculate the equilibrium constant, and if you have a large number or a small value, it will tell you that when this thing reaches equilibrium, what you would mainly expect to have. What is considered a large value? It is the large value of 1 and above. So anything above 1 is considered a large value for equilibrium constants. Anything that's less than 1 would be a small value. So when we have our equilibrium constant, it is only affected by temperature. And what I mean by that is it is a constant value as long as you do this reaction and keep the temperature constant. So you could do this reaction and let it reach equilibrium, and you could calculate K, and you'll get the same value as long as the temperature stays the same if you did it like 200 times in 200 different ways. And what I mean by that is you could start with all reactants in one case. You could start with all products. You could do a little bit of everybody. It will always come to rest at the same ratio of products to reactants. You'll always get the same number as long as you don't change the temperature. And you might say, well, how could that be if you start with different amounts of everything? How does it come to the same number? So if you just think about it, a simple example of that, which is, for example, let's say we wanted to end up with a K value of 2, right? I could get 2 by having a ratio of 8 to 4, right? That equals 2. I could have a ratio of 4 to 2, that equals 2. I could have a ratio of 2 to 1. That equals 2, right? Those are all different numbers, different values and stuff like that. But the ratio of the products to the reactants or the numerator to the denominator are all the same. And you end up with the same number. So it's a very hard concept in terms of equilibrium, which means people think, well, you start with different amounts, you should get like a different K value. But you'll always get the same ratio of products to reactants as long as you don't change the temperature. If you do change the temperature and you looked at a K value, for example, at 25 degrees Celsius versus a K value at 40 degrees Celsius, these K values will be different. And the temperature plays a role in that, and you will end up with a different value of K. But if you did a bunch of reactions at 40 degrees Celsius and you calculated K for all those reactions, they all should be the same number. And if you did a bunch of reactions at 25 degrees Celsius and calculate K value, they all should be the same number. But if you compare the K value at 25 to the K value of 40, they will be different numbers because the temperature is different, and you'll end up with a different ratio because of the temperature being different. Any questions on that there? All right. In terms of a reaction that reaches chemical equilibrium, when you look at it, for example, in the beaker, it may just look done to you. It may look like there's nothing happening. The reaction's over. But because this is an equilibrium reaction, if you were able to like super zoom down to the molecular level, you would see a lot of activity of reactants going to products going to reactants to maintain whatever color you're looking at, like a red color, no color, whatever it may be. But there's a lot of activity happening below the surface. But when you look at it sort of on the large scale, it may look like nothing's happening, but there's this continuously back and forth that's happening to keep this guy at equilibrium when you look at this type of reaction. Any questions on that? So this brings us to Le Chatelier's principle, which is the idea of you have a system at equilibrium. So you have the system at equilibrium. And then you decide to do something to it, which is you add a stress to it. And what that does is it frankly screws up the equilibrium. So you do something and you screw up the equilibrium, which means it is no longer going back and forth at the same rate. It's going one way or the other. But because this is an equilibrium reaction, it is going to want to self-correct itself. And it's going to self-correct itself by doing one of three things usually. It may correct itself by shifting to the right, which means you're going to make more products. It may correct itself by shifting to the left, which means you'll make more reactants. And frankly, there are certain situations that even though you did something to it, not much is going to happen. So there's still going to be no change that's going to occur. So what are the stresses that you could do to a system that's at equilibrium? You could do something with concentration. You could either add or remove. You could do something with pressure or volume. You could do something with temperature, which is either increase it or decrease. Or you could add a catalyst to the situation. So these are some common stresses that you could do to a system that is at equilibrium. And depending on what you do to it as to what will happen. So we'll start with concentration here. When we look at concentration, there's really two things that you could do. You could either add more or you could remove. And when we add, it will always shift away from the side we added it to. And when we remove, it will go actually towards the side we removed it from. And when we talk about forward and to the right and to the left, we're really talking about the equation we're looking at as to reactants or product side of it. So for example here, let's say we had a nice system at equilibrium here, also known as stick figures 101. It's advanced stick figures. They have faces. You don't get that in the beginning class. You gotta get those advanced ones. We're gonna call this guy on the right here reactant. This guy on the my left and right backwards there. My left reactants, my right products here. And in this case, what's gonna happen is we're gonna have somebody hop on over here on the product side. So when somebody hops on the product side, we get this situation here. And it was at equilibrium. And now clearly we screwed up the equilibrium here, right? By that guy hopping on the right. To fix it, do we need to put more people on the left or the right-hand side? Yeah, we got to go away from the side we added it to, right? So away from that side, we need to put more people over there on the left. it will once again get back to an equilibrium state here. I didn't say I passed stick figures, by the way. I just said I took it. Yeah. And now we're back to an equilibrium sort of state in that case. Now, if we look at this same sort of starting situation here, and once again, our guy here on the right or left, there is our reactants. I'll get that right and left down eventually. And our guy here on our right is our products. Let's say this guy decides, I'm just going to hop off, right? So when he hops off, we're going to get this situation, right, that occurs. Not so good. Now to fix this equilibrium, we need more people on the left or right. Yeah, we got to go towards the place where we removed it, right? And put some more people over here, and we will come back to equilibrium in this case, and back to equilibrium. So when we add something, it will always go away from the side we added, which means if we add more reactants, it will shift to the products. And if we add more products, it will shift to the reactants. The reason really for that is, for example, if we have this reaction, and if I add more A, what that means is there's a lot more reactants available to react with each other. And that's going to actually kick off the forward direction, which means we're going to make more products. Now, if I add more D, for example, there would be a lot more products swimming around, and they're going to find each other a lot quicker. And that's going to kick off the reverse reaction, again, away from whichever side you added to. When we remove something, if we had to say a reaction like this, and I take away some products, you could think of it as like making a hole on the product side, right? So it's got to fill the hole. So it's going to go towards the product side here to fill the hole. The real reason is actually the same reason. When you remove products, you now have a lot more reactants. So they're going to start reacting and going towards the product side and actually go towards the side you removed it from. So when we have concentration, we will either add or remove. To add something in a reaction, it's very simple. You can go to the shelf and you basically just grab it off the shelf, something that has that ion in it, squirt it into the beaker, and you added more of it, right? So say you had sodium in there, you go and add some more sodium and it will go one way, or more iron, you can add something that has iron in it and it'll go one way. To remove something from a beaker that has ions floating around, you just reach in and grab it out. You do not. You actually could add something that will to this that is not part of the reaction but can react with somebody, and you can make a solid. And a solid is not including the equilibrium constant, so that's essentially like going in there and grabbing it out of the solution. By making the solid, it will actually take it out of the solution and cause the equilibrium to shift one way or the other. Any questions on that? Yeah. Honestly, it depends on the situation. You don't really need a lot in a lot of situations. You can just add a little bit and it's enough to have a shift. If you add more, it will shift even more. So there's a lot of ways you can do it. A lot of times, if you're doing it, say in the laboratory, a lot of times there are colors that sometimes develop from reactants to, say, products. So for example, you could do one with like, for example, you could do something like this, iron 3 plus a little thiocyanate, and we'll make this like complex ion type guy, right? And this guy over here is like dark red, and this guy over here is yellow. So for example, if you made this equilibrium, maybe you're somewhere in between like an orangey type color, and you could add, for example, more iron, and it will cause it to go to the right, and you would see your color and your test tube go from like a more orangey to a darker red, and you know you're kind of moving to the right. You could go also push it back the other way. You could add something that takes away some silver, which would take away that and cause it to go back the other way, and it'll go from like dark red back to yellow. Actually, in a lot of cases, just a few drops in a situation, if you have like test tubes and stuff, is enough to get it to go one way or the other. And that's usually a lot of times when you do something with Le Chatelier's principle, there's some type of color that you can see on one side versus the other. So you can kind of visually see sort of which way is shifting. If you had something that was all colorless, you would have to really just do your calculations and just kind of know that perhaps that's what's happening. But a lot of times there's colors associated with one way or the other, and you can kind of use that to help you guide it. Other questions? Yeah.
Removing the reactants shifts it towards the reactant.
It would. So for example, if I had this one in a test tube, this equilibrium, which means I basically will have all these guys floating around in there. And if I took some silver, for example, the silver will actually react with the thiocyanate and it will make this like white solid. And that would essentially be like removing a reactant, which means it will actually shift that way towards the reactant side. And you'll actually see it become, for example, more yellow. It'll get a little cloudy too, because you're actually making a solid in this case, but it'll become lighter in terms of this color. Other questions? All right, we'll lay it up there.